So next let's do the flux through the right and left faces. So we know our electric field, we know it has an x component, a z component, the y component of 0 is 0. Let's pick our dA vector, and then we'll put together the A with the E, bearing in mind that when we're at the right face, we know what the value of x is, and we're going to plug that in for our electric field. So let's do the area vector first. So our right face is this one. On this guy, this is the area of the face. Why don't we talk about that electric field first? So the electric field is the magnitude 2 times 10 to the 4 times x. When we're at the right face, so everywhere on this face is right here, is at x equals a. So E, where x equals a, is E is 2.0 times 10 to the 4 times the x value, which is a, which is 10 centimeters, times I plus k. Our electric field here is going to be constant. So our electric field still has an x part and a y part, or a z part, but the electric field is constant because everywhere on this right face, the x value is constant, and when we put in that constant value into the electric field, we get a constant electric field. If we have a constant electric field, then we don't need to use the integral form for our flux. We can do it if we want to. So if we started with the integral form, we'd have the integral of E dot dA. Our electric field is constant, that could come outside the E, so we get E outside of the integral of dA. The integral of dA is just A. So it boils down to the same form that we had before. So we'll do our form where we do EX times AX plus EY times AY plus EZ times AZ. We know right off the bat that this term is going to be 0 because EY is 0. Our area vector sticks straight out of the face, so there's our area vector. Area has a length times width, 0.10 times 0.10. It's the magnitude of the area. The direction is out of the face, that's the x direction, so we have in the I direction. So for the right face, this is our AX, and our AY and our AZ are 0. So AY is 0, AZ is 0. So that term is also gone. So now we have EX times AX. EX is 2 times 10 to the 3. AX is 0.1 times 0.1, 0.01 meters squared. Multiply this out in the calculator, and we get 20 newtons per coulomb times meters squared. Again, no direction here because electric flux is a scalar. So that's the flux through the right face. Let's also do the flux through the left face. So when we redraw our cube, let's think at the left face, do we know what the value of x is? So there's x, there's z, there's y. Our left face is right here. On our left face, x is equal to 0 everywhere because that left face is lined up along the yz plane. So at the left face, x equals 0. So our electric field vector is 2 times 10 to the 4 times 0, I plus k. So our electric field everywhere is 0. Our net electric flux is the integral of E dot dA. So that's the integral of 0 dot dA equals 0. So our net flux through the left face is going to be 0. So next we'll do the top and bottom faces, and then we'll be able to clue up and find the net flux.